Hi, I'm Kayla, and this is my Lab 3 summary. For the setup, one must understand the technique for beam expansion. Here we use a Keplerian beam expander to decrease the measured beam waves by a factor of 10. It may seem counterintuitive to use a beam expander to create a reduced beam diameter. However, beam diameter and divergence angle are inversely proportional, so at a distance far from the laser aperture, using an expander actually results in a smaller diameter beam. The bottom figure shows the setup used for both the beam expansion and the beam profiling to determine if the 1/10 magnification factor was achieved. This shows the setup. It contains the same elements drawn for the beam expansion. To align the system, it's easiest to do so starting with the last element. So after aligning the laser, align the focusing lens first. After that's aligned, move it out of the way and align the achromat. This makes it easier since you can block the components already aligned without blocking the beam path, effectively reducing the number of reflections when trying to insert and align new components. The following selections were made for the components. Since a 0.25 numerical aperture was selected, the collimating lens's focal length had to be at least 10 times longer than that of the objective to achieve the desired beam expansion. Using the equation shown, the ideal spatial filter diameter would have been 22.6 microns. The same 200 millimeter plano convex lens was used from last week for focusing the exiting expanded collimated beam. To create a clean beam going through the achromat, a spatial filter was used. The spatial filter is placed at the intermediate image plane between the objective and collimation lens of the beam expander, since this location is conducive to filtering, since the laser's energy comes to focus at that spot. An ideal filter would pass about 99.3% of the light and would have a 22.6 micron diameter for the setup. A 50 micron filter was actually used because the output with 25 didn't look Gaussian enough. This video shows some of the adjustments to get the spot to be most intense through the filter. Only about 35% of the incident power is measured after the expander though, and not 99.3%. This may have been partially due to the way the objective treated the beam, since it sent it a little low and part of the light was getting blocked before reaching the detector. After alignment, the collimation of the beam had to be checked. This is done using a shear plate. The wedge shear plate creates two reflections in the beam. These beams interfere and create dark fringes or bright fringes where they constructively interfere and dark ones where they destructively interfere. When the incoming beam is collimated, the fringes will be parallel to the reference line. When it's not, the optical path difference between the interfering waves will not be zero, causing a tilt in the fringes with respect to the reference line. The video shows how translating the achromat along the optical rail moves it through the range where the output beam goes from collimated to no longer collimated. The same procedure is used as last week to profile the beam. After focusing the lens, a knife edge is passed through the beam and the corresponding power to the knife displacement was recorded. This is done on both sides of the beam's focus. From this data, the beam diameter at the focus can be calculated, and it can be determined if the beam diameter is reduced by a factor of 10.